Hello, everybody, for the clip 3 of the first part of wireless communication, modern wireless communication. The first part is the fundamentals, and this is clip 3 of that part. In clip 2, we reached to this slide where we represent the general form of a sinusoidal signal, and we said that we use the sinusoid signal, cosine or sine, for modulation. So it is the modulating signal, and we also explained the reason, and we said that this signal is the stem of all other signals. Sorry, because it consists only of a direct delta which has bandwidth of 0, and the direct delta at exactly at the frequency of the cosine signal, which is given by f0. And sorry, and also we mentioned that we have three kinds of modulation, because we have three parameters that we can change in this sinusoidal signal, which is the amplitude and frequency and phase. So if we look to these possible modulations, so we have amplitude modulation, which means that you can see that the amplitude A is now function in our information signal x of t. So the magnitude or the amplitude of this cosine will be changing according to the changes of our information. So this will be some kind of transmission or some modulating of our signal with the carrier frequency f0. And then we have also frequency modulation, as you can see it here. And you can see now the frequency is not fixed anymore, but the frequency is function in the information signal, in our information signal x of t. So the frequency itself will be changing according to the changes of the fluctuations of our information signal. And phase modulation, it is, you can see that the magnitude now or the amplitude is fixed, frequency is fixed, but now the phase of the sinusoid signal will be changing according to the information signal. So this is the three main kinds of modulation. Also, we can have hybrid between different parameters. For example, we have the amplitude phase modulation, where the information signal can be like divided into two parts. One part is modulated in the or augmented in the magnitude or the amplitude of the sinusoid signal, and the other part in the phase of the signal. This is very widely used in digital communication, and we call it QAM signal or quadrature amplitude modulation, as we will explain it in details in the digital communication part. So those are the basic kinds of modulation. In this course, as we mentioned, that we try to cover things like not very deep, but also not superficial. So we try to compromise between those things. So we try in this part just to explain the amplitude modulation, just to have a sense what modulation means. And when we come to the digital communication part, we can more a little bit more in deeper way about the digital modulation techniques. Okay, now we take a simple amplitude modulation. Maybe the simplest form of the amplitude modulation is just by the multiplication of information signal x of t, or the baseband, by the carrier signal is the cosine 2 by f0 t. So this could be seen as the simplest form of amplitude modulation. Okay, x of t, it can be analog signal or it can be also digital signal. It can be symbols or it can be like analog signal represents exactly the original signal without like analog to digital converter, as we will see in the digital part, digital communication part. So now this is the multiplication of x of t, as you can see, multiplied by cosine 2 by f0 t. Okay, so you can see in this shape on this figure that we assume that we have this blue signal is our information signal, maybe signal of voice or whatever, or from certain sensor, maybe temperature sensor, pressure sensor, and then we have these signals. You can see that they are changing in time. Now we are talking about analog communication, so there is no conversion to digital symbols, and now we have this is x of t. This is the information signal, or the signal that we want to transmit in general, and it is multiplied by cosine 2 by f0t, and then we got the modulated signal y of t. You can see here this is the cosine, so it has very high frequency, but just I made here zoom to see that it is just a sinusoid signal, as you can see it here. And now after this multiplication, we will have the modulated signal y of t, which is shown here. Okay, so now by making this modulating of the original signal, of the signal that we want to transmit, we have now the signal is ready to be transmitted. Of course, we might use, for example, RF amplifier, or maybe up converter to have higher frequency. Remember only here that usually the carrier frequency should be much greater than the bandwidth of the signal. So this is a general. Of course, we have some like systems, exceptional systems like in ultra wideband, which is not necessarily true, but in general, most of the communication systems that we have, the carrier frequency should be much greater than the bandwidth of the signal that we want to transmit. Okay. um, there is a nice Fourier transform property. It says that it can be approved actually mathematically, but it is not here. We will not give it here, but you can find it. It is just one line of a proof. So it says that the multiplication of any signal in time domain x of t, if you multiply it by cosine 2 by f0 t, what will happen is that the result will be shift in the frequency domain. This is this is in frequency domain. This is frequency domain, and this is in the time domain. Okay. So, sorry. Yeah. So the multiplication in time domain, for a signal in time domain multiplied by cosine in frequency domain, it will be the shift of the frequency transform of x of t, or Fourier transform of x of t, which is, of course, we call it like x of f, but x capital. Okay. So it will be the shift of x of f to the right and to the left by amount of the carrier frequency f0. This result is very important in modulation. This means that, assume that this is x of f, the frequency domain of the x of t. X of t, it can be, as we mentioned, our voice, for example, after microphone. So we have electrical signal, which changes according in the same way like the original signal, voice signal. Okay. Now this signal in time domain, it is continuous in time domain, as we know. So it can be, as we showed before, so it can be like just signal like that in time domain. However, as we said, that if we take the Bose spectral density of the signal, then we can see it how it looks in frequency domain. So it can be in frequency domain in this shape. This is just for simplification. So for the simplification, that we make it like symbol, like triangle, as you can see. And now this is x of f. Okay. Now if we after the multiplication of x of t by cosine, the frequency domain will be this one, but shifted to the right and to the left. Okay, so it will be shifted in this way, and shifted by the amount of the frequency f0 is the same frequency of the cosine signal or the sine signal. Okay. Actually, there's one nice property here, that why we make this mirror that in negative frequency. So usually we have only positive frequency, we don't have negative frequency. But actually this the imagination that we have like mirror in the negative part, it came from this property, because when we make them this multiplication, we will have like double of the signal. This is the original signal, okay, at f0, but we will have it is mirror in the other side. Okay, so it will be, this is the mirror, it is like on mirror. Okay, because of that, we imagine that the signal itself, it has already some like mirror on the negative frequency side. Okay, and yes, so this is the basic multiplication of any signal with cosine. In analog communication, we call this as double sideband suppressed carrier modulation. Double sideband suppressed carrier modulation, and we call it like this because we have double sided of the original information, but the carrier itself, it disappears. So we don't have the carrier as a separate signal here, but we have this only the double sided of the original signal. Okay, so you can see here how to demodulate the signal. If you remember that we said once we have a modulation, the modulation must be reversible operation. It means that we should be able to retrieve our original signal x of t at the receiver part. Okay, so there is a basic math, trigonometric property. It says that if you take the cosine of any cosine of ax, for any ax, so we have cosine ax square, or if you multiply cosine ax by another cosine ax, this could be like expanded like half plus half times cosine 2ax. So this is a property in for the sinusoidal signals, or for the cosine and sine. And now if we multiply this, you can see this is now the received signal y of t. Y of t is the original information x of t multiplied by cosine. What we need to do, just simply multiply it by another cosine, multiply it by the same carrier. So it means that if we multiply another time by the same carrier, we will be able to receive or to retrieve the original signal, as you can see here. So we multiply y of t by cosine 2 by f0 t. So and we know that y of t is nothing but x of t multiplied by cosine. So it becomes like x of t times cosine times cosine. It becomes x of t times cosine square, and cosine square can be expanded like half plus half cosine 2ax, which means that it will be half times x of t, it is x of t divided by 2, plus x of t divided by 2 times cosine 2 by 2f0. Now we have 2f0 because we have here 2. So it means that the original signal will be shifted even more. So this part of the signal actually is very high frequency component, which could be easily removed by using low pass filter. So we can remove that part. And this part is a scaled version of the original signal. So it will be the same original signal, but it is like attenuated by half. Of course, using some amplifier, we can get the signal again. So now we have y of t, just we multiply it by the same carrier frequency, or the carrier signal. We get y1 of t, and then use low pass filter. Here, low pass filter, we will get our original signal again. This is, of course, we talk ideally now. Remember that in a practical system, many times we don't have the original, or we cannot generate exactly the same original signal cosine 2 by f0 t. There will be some like drift in the frequency, or also because of the propagation properties, that the received signal or the received carrier will be shifted by the Doppler frequency of if the receiver or the transmitter, or even there is something in the environment moving, then we might have Doppler frequency, which makes shift in the frequency, and this makes the demodulation process not perfect. But still, we can use some techniques like phase-locked loop, and we can use some techniques that we can still capture the original signal, which can be very close to the original transmitted signal. So this is the simplest kind of modulation and demodulation. So the main objective here, just for you to know how to make the modulated signal and how to demodulate it. So we modulate it, means that we take the original signal, we carry it over carrier, and this is called the carrier signal, is usually sinusoidal signal, and we can carry it over like amplitude or frequency, or it is phase, and we transmit it, and in the receiver we can do the reverse operation, and it is called demodulation, and then we receive our signal again. Okay, this is in frequency domain, the same concept but in frequency domain. Let us take this example to explain uh, um, one application of the modulation. Assume that we have three signals, for example, x1, x2, and x3. Okay, and those three signals that we want to send them over the same channel, for example, over the same line or coaxial cable, or over the same wireless channel, or whatever. So we want to send three signals over the same, exactly over the same channel. Each signal here, we assume that it is maximum frequency is 3 kilohertz. Okay, and how can we send them together without making interference between each other? This is called multiple access. Multiple access, which means that they are three different signals from different sources. We want to send them over the same line, okay, over the same media, and in the receiver we want to be able to like isolate all of them. Of course, if you just send them over each other, they will interfere each other, and it will not be possible to receive them anymore. Okay, so now we want to use the same concept of modulation, of multiplication modulation, or the as we have seen, double side band subcarrier modulation. We want to use the same concept in order to transmit these three signals together. Okay, the idea simply is like that. So assume that this is the Bose spectral density of the signals for x1, x2, and x3, the magnitude, and then you can see that if each signal it has 3 kilohertz bandwidth, it means that the maximum is 3 kilohertz. Okay, and as we said, this is the mirror of the original bandwidth of the signal, and now we can send the first signal in its baseband. Okay, so this is the first signal. So we send the first signal in its baseband. Okay, and for the second signal, we can shift the spectrum of the second signal to be after the first signal. Now, here we assume that our communication media or channel, it has a bandwidth of 18 kilohertz. So we have enough bandwidth to send these three signals. So what we can do here, we multiply x2 by cosine 2 by f1t. How to select f1? We should select f1 to guarantee there is no interference between both signals. So simply, if we put it like 7 kilohertz, if we put f1 equal to 7 kilohertz, what will happen? This signal, the original signal, will be shifted. This is for x2, will be shifted by 7 kilohertz. Okay, it is 7 here because after the modulation we will have double side band, so we will have the double sided here. So it is 7, but the original signal is only 3 kilohertz. So 7 minus 3 is 4, and 7 plus 3 is 10. So this signal will y2, or the second signal, will occupy this band from 4 up to 10 kilohertz. But the original signal has up to 3. So actually we have some difference as a guard or as a protection, so we don't have interference between those two signals. Okay, and for the third signal we have to shift it to guarantee that it will not interfere between the previous two signals. Okay, the previous signal ended at 10. Then if we shift it the third signal by 14 kilohertz, so 14 minus 3 is 11, and 14 plus 3 is 17. So still 17 is less than 18 is the bandwidth of the channel, but still we can have also protection between the third signal and the second signal. So by this very simple concept, we were able to send three signals in the same line without interfering each other. So this is a simple way that this is the multiple access, or also it is called multiplexing in some cases. We will talk about this later when we talk about in digital communication, what is the difference between multiplexing and multiple access. Okay, how to make the demodulation? The demodulation simply, again, when we multiply in the same carrier frequency or the same carrier signal, we can have the shift to very high frequency, which can be suppressed by low pass filter, and lower frequency, which means that it is our signal. And this is y of t, this is the received signal. For the first signal, of course, what we need, you can see, for the first signal, we can to retrieve our first signal, we just use low pass filter. So by using low pass filter, we will have our x1 of t. So low pass filter at 3 kilohertz. So we have x1. Okay. For the second signal, first we use band pass filter. So the band pass filter, just we want to have this signal with using some band pass filter. Okay. And then using the multiplication, as you can see it, with the 7 kilohertz. So we have shift to the right, shift to the left. For the shift to the left, it means that it is our original signal. By using low pass filter, we got x2 of t, and for the higher frequency, it will be suppressed by this low pass filter, and the same concept will be done for the third signal. So this is a simple way how to make the demodulation process for this simple system. Okay, now we talk about noise and interference. Noise is any undesirable and meaningless random signal which bothering our information signal. So actually, noise is the major reason for performance degradation in communication. So noise uh, uh, is the parameter which actually limits the capacity that we can achieve in communication system. Okay, so noise, we cannot get rid of noise because noise is completely like unpredictable signal. It generates from like thermal noise or shot noise. It is random by nature. So we call it that. It is autocorrelation is direct delta, which means that it is uncorrelated signal. Then it cannot be like predicted. It cannot be predicted how it will be. Since it is unpredictable, then we cannot cancel it or we cannot remove it. Okay, and it limits the performance of our wireless or wireline communication. Noise is not only external, because noise can be like received from outside, but the most important part is the noise which is generated internally, because every electronic component will generate some kind of noise. Every resistor, every conductor, it will generate noise. Even every transistor or semiconductor in general, it will generate what is known as like shot noise. So noise is always there. We cannot get rid of noise, and we have to deal with it. And in order to know what is our limitation, how much we can achieve in this communication system because of the existence of noise. Okay, and interference is also for us random like noise, but it might have a meaning. For example, if we have another transmitter sending some signal, so that signal, it can bother our transmission as well. It can also degrade the system performance. But the difference between interference and noise, that interference, sometimes we can deal with it. So we have some interference cancellation techniques. For example, interference, it might come from certain direction of arrival, so we can use beamforming to reduce the signal coming from certain different direction than our signal, or we can use successive cancellation techniques that because the interference itself, it has meaning. So if we have access to this interference signal, and we can predict it, so we can reduce or cancel it from our signal. information. So it is different. The interference is different than noise, but generally it has similar effects, both of them. About noise, we have two kinds mainly of noise in digital communication or in communication, in electronic communication in general. Either thermal noise. Thermal noise is generated because of the random movements of electrons inside any conductor. You know that when you have like conductor and then this conductor, it has the temperature of the ambient temperature. Because of the ambient temperature, the electrons inside, so they have energy and they will like move in completely random way. So when the electrons in one side is more than the electrons in other side, of course we will have voltage drop there. So if you have very sensitive voltmeter, you can see that there is noise generated. So there is a voltage across any resistor or any conductor. This noise usually can be represented as a Gaussian distribution. The probability distribution function of this noise is Gaussian distribution with zero mean, and it has RMS value. It can be computed, but we will not give the equations here. For the thermal noise is always exists, even for example, for any conductor or a resistor, even if it is not connected to anything, there is a voltage drop because of the thermal noise. Shot noise is different kind of noise, that because the electrons moving are discrete charges, so they are not smooth 100%, and when they are moving across the cross sectional area, they can be like hit each other, or it can have some kind of discontinuity, which we can see that as a noise because it is not 100% smooth, and this can be observed like in semiconductors. So because in normal conductors, like in wires or in resistors, this can be like completely random in both directions and cancel each other. But in semiconductors junction, so we can see it clearly, this is the shot noise. And the difference between shot noise and thermal noise, that thermal noise is always there, but shot noise observed when there is a current flow. Okay. So in any electronic device that we use to design transmitter and receiver, we should keep in mind about the noise, and because the noise will determine the sensitivity of the receiver. So the sensitivity of the receiver depends on noise. Why? Because you will not be able to receive a signal power which is like considerably less than the average noise power of that receiver. Okay, so usually we have the signal to noise ratio at the input of the receiver should be high enough to detect the signal. If the signal is considerably less than the noise, then of course the receiver will not be able to detect that signal, because it is under the floor, the noise floor of that signal. Which noise? Noise which is generated inside the receiver itself. This is one reason that why the front end amplifier should be designed very carefully to have very low noise properties, or low noise figure. Okay, now we talk a little bit about the channels. In telecommunication, is the channel actually is the connection between the transmitter up to the receiver. Okay, the channels can be wireline, like coaxial connection, can be fiber optic or waveguide, and it can be wireless channel, like in cellular networks, Wi-Fi, Bluetooth, satellite networks, microwave links, and so on. Okay. The wireless channels actually means free to move of the transmitters and or the receivers, and this is the reason that wireless communication is the most desirable kind of communication. However, we have a lot of critical challenges associated with wireless communication, because it is shared between all systems and users. It is not like the cable. because if you have like cable for every transmitter and receiver, they will be physically isolated. But in wireless communication, you mount your antenna and you start to propagate your signal, and everyone propagating in the same media, so it is shared. So multiple, very careful multiple access techniques must be used. We have also noise and interference signals, not only the internal noise but also external noise coming from different sources. For example, your mixer, electrical mixer at home, or like from if you are close to some substation, there is some electromagnetic interference coming from there. So we have a lot, many kinds of noise signals. Um, in wireless communication, we have very large signal attenuation. We have problem of multibaths, so multibath reception. So when you send a signal, it will not reach just from the transmitter to the receiver, but it can come, it can hit different objects and then reflected from those objects and comes to in multibath, which can cause like serious problems called like intersymbol interference, and we will see them later. We can have also fading, random fading, and different kind of behaviors. Actually, we will see them in more details during this course. Okay, now if we talk about free space wireless communication, I'm not going again to in deep analysis, but just to keep it like a very simple way, assume that you have your transmitter here. Okay, you have transmitter antenna. Okay, this is your transmitter, and you start to and you feed power b bt. Bt is that your power transmitted in space. Okay, this if your antenna is like isotropic, it means that it propagates everywhere, so uniformly, then the power will go in this way. So and now you can assume that it is like ball surface, it is like ball surface. And now if you are like in a distance r, in a distance, or let's say it is d, at a distance d from the source, sorry, okay, you are at distance d from your source. So what will be the area of the ball? Okay, the area of the ball which has radius of d. So this area will be 4 by d square. This is the area of ball with which has like radius d. Okay, now you have the transmitted power is bt. Okay, what is the power density over that ball? Now I am talking ideally. Okay, what is the power density? Power density will be simply like bt, transmitted power, divided by the area, 4 by d square. We assumed now there is no absorption of the signal, and the signal, it will all the transmitted signal will arrive to the distance d from your transmitter. So it will be bt over, let me just correct this one. Okay, yes, okay, anyhow, so it will be like bt divided by 4 by d square. And what is the unit of this value? It will be watt per meter square, because it is a power density now. Okay, how much power you can get over at a distance d? So if you have receiving antenna here, okay, if you have a receiving antenna here, how much power you can extract from this power? It depends on the antenna area. Okay, but not physical area, not needed to be physical area. This is ideally, it will be the physical area, but in reality it is called the effective area of the antenna. The effective area of the antenna, if we call it like a, is equal to the gain times lambda square. Lambda is the wavelength. We talked about this in the previous clip. So it is lambda square divided by 4 pi. For all antennas, this relation is valid. Okay, so it is the antenna gain multiplied by lambda square divided by 4 pi. So if you use this, multiply this effective area in this power density, you will get, this is the received power. So the received power actually is the transmitted power times, here we put that transmitted antenna gain. So if your antenna is not isotropic, so it has some directivity, so you should use JT. If it is isotropic, use 1 multiplied by the gain of the receiver antenna multiplied by lambda squared. It comes from here, divided by 4 by d square. Of course, here 4 by d actually it is like this, because all square, because we have already 4 by here. So the received power is equal to the transmitted power, okay, multiplied by the transmitting antenna gain multiplied by the receiving antenna gain divided by the losses. And you can see in the free space the losses is related to the distance square. For example, if you are away like 100 meter from the transmitter, then the losses will be related to 1 over 100 square, which will be 1 over 10,000. So the power, the received power, will be attenuated by up to 1 by 10,000. So this is the reason that the wireless communication, it has very high attenuation. So, and actually, by the way, this is the simplest channel model, which is useful only in the free space. So if we don't have buildings and we don't have multibaths. But this model is not accurate when we want to model the channel, for example, in cellular network, in mobile network, or in your Bluetooth device. It is not valid, or it is not accurate actually model to be used. Okay, in this case actually, okay, so in this case, in the case of multibaths, here we have the two bath or two rays channel model. So the received power, will be related to the transmitted power, with actually the distance between the transmitter to the receiver of the power 4. So it is even much worse than the free space model. It is the gain of the receiver times the gain of the transmitter times the height of the receiver square, the height of the transmitter square, and divided by d of the power 4. But anyhow, we can actually in practice we can ignore these. We can put here just some number to represent these values, because actually we have many other like problems in the channel, not only the distance. So we have absorption, we have scattering, we have multi-baths, mini baths, not only two baths, and it is more like accurate to represent this relation as like stochastic relation, not deterministic relation. And in that case, we say that the received power equal to like some random number, okay, multiplied the transmitted power divided by d of the power 4. So here we have some random number depends on it can be like a log normal distribution, in case, or if we take only the large objects attenuation in the channel. And actually also we when we talk about digital communication, and about the problems of the channel in digital communication, we will see more about these properties. If we see this example, so if we have a system where assuming that the channel gain, the antenna gain of the receiver and the transmitter and the height, all of them equal to 1, and if the transmitter transmits with power 1 watt, and we want to see how much you can receive if your receiver is only 100 meter away from the transmitter. So you have transmitter let's say Wi-Fi sending at power of 1 watt, and after 100 meter, how much power you will be able to see from that transmitter. Okay, based on the previous equation, the power received equal to power transmitted times these values, all of them they are 1, and divided by 100 of the power 4. So the power is very, very small, as you can see it here. It is 1, 2, 3, 4, 5, 6, 7. It is zero point 0.1 microwatt. Zero point 0.1 microwatt. So it is very, very small power that you can receive from that transmitter. And usually in communication, actually, we deal with dBm, so we don't deal with the actual value in this way, because it is hard to say. As you can see me now, I was counting how many zero we have. So usually we take the power received in dBm, and in dBm we take the 10 log 10 for base 10, the received power, and we divide it by 10 of the power minus 3 to convert it to the m. It means that dB per milliwatt, because 10 of the power minus 3 is 1 milliwatt. So we divide them, so we got minus 50 dBm. So minus 50 dBm, it means that minus 50 dB according to 1 milliwatt. Okay. uh, Channel fading. Okay, now maybe we will talk about the channel fading in the next clip. So now we have already close to 40 minutes, so we stop here and we continue in the fourth clip of this fundamental part in this course. See you. Thank you.